Hello, my name is Patel, and today I'll be talking about dysregulated energy metabolism and Alzheimer's disease. Alzheimer's disease is one of the top 10 causes of death among the elderly. As of 2018, there are 5.7 million people living with Alzheimer's disease. Furthermore, as of 2015, more than 100,000 people have died of Alzheimer's disease, which may be an underestimate because of the way cause of death is not documented. In Alzheimer's disease patients, cognitive function declines as amyloid plaques accumulate. Amyloid plaques are an accumulation of a protein known as amyloid outside of the neurons, as shown in the figure. In addition to accumulation of amyloid plaques, neuronal synapses decrease in the cerebral cortex and the hippocampus of Alzheimer's disease patients. The figure shows that these areas are known to shrink in Alzheimer's disease patients. In addition to decreased neuronal synapses, and metabolism is dysregulated in Alzheimer's disease patients. Metabolism is dysregulated secondary to altered enzyme, transporters, receptors, and cofactors activity related to lipid, glucose, and glutamate metabolism. Glucose metabolism is also known as glycolysis. In elderly individuals, glycolysis decreases by 10 to 15%. In Alzheimer's disease, glycolysis decreases by 20 to 25%. In Alzheimer's disease patients, glycolysis decreases, but glucose concentrations continue to increase outside of the neurons. This is because of decreased GLUT3, which is a glucose transporter, and because of decreased glycolytic enzymes activity. On the screen, the figure shows that as GLUT3 is downregulated, less glucose is taken into the cell. This leads to reduced neuronal activity, reduced metabolism, and reduced cognitive function. It also shows that neurodegeneration is also a result of decreased GLUT3 concentration. In other words, GLUT3 concentration decreasing leads to increased amyloid plaque accumulation. Amyloid plaque accumulation also increases due to decreased enzyme activity of glycolytic enzymes such as hexokinase, pyruvate kinase, and phosphofructokinase. These are three enzymes that play a key role in the rate-limiting step of glycolysis. The figure on the screen shows that as the enzyme activity is inhibited, neuronal cell death is promoted, and amyloid plaque accumulation is also promoted. Amyloid plaque accumulation can further inhibit the enzyme activity. In addition to glucose metabolism being dysregulated in Alzheimer's disease patients, lipid metabolism is also dysregulated. Two enzymes or proteins that play a key role in lipid metabolism are ACOT7 and APO. ACOT7 hydrolyzes free fatty acids. In mice with ACOT7 mutations or knockouts, free fatty acid levels accumulate, leading to neurodegeneration. APO is a protein that associates with cholesterol and promotes amyloid plaque accumulation. The figure on the screen shows overexpression and underexpression of APO4. For example, overexpression of APO4 promotes amyloid plaque accumulation. Lipid metabolism also decreases with vitamin deficiency. Vitamins serve as cofactors for many metabolic pathways. Here we see that folate, vitamin D, and vitamin E are three of the vitamins that are related to amyloid plaque accumulation. Vitamin deficiency can be addressed by vitamin supplements such as vitamin E supplements, vitamin D supplements, and folate supplements. Folate and vitamin D supplements have been promising, but vitamin E supplements have been showing mixed results in Alzheimer's disease patients. A byproduct of lipid metabolism is ketones, and ketones can be metabolized through a process known as catalysis. Catalysis requires less NAD+, which is an electron acceptor. So when there's less NAD+, cognitive function decreases. But ketolysis is known to replenish NAD plus supplements because it requires less NAD plus compared to glycolysis. And ketolytic diets can be induced in Alzheimer's mice and Alzheimer's patients, which have shown promising results. However, ketolysis or ketone diets are not yet a treatment option because long-term effects of ketones are unknown. The figure on the screen shows that glycolysis and ketolysis can produce ATP. The one thing that stands out is glycolysis requires 4 NAD+, but ketolysis only requires 1 NAD+. As mentioned earlier, the less NAD+ there is present, the more cognitive decline there is. In addition to glucose and lipid metabolism being dysregulated, glutamate metabolism is also dysregulated in Alzheimer's disease patients. GLUT1 is a glutamate transporter common in neurons. As GLUT1 concentrations decrease, amyloid plaque accumulation increases in Alzheimer's disease patients. The figure on the screen shows data from a mice study. The x-axis shows the 3 regions of the hippocampus that were studied, CA1, CA3, and DG. CA1 and CA3 stand for the first and the third regions of the hippocampus respectively. The DG stands for the dentate gyrus. The y-axis represents the amount of area occupied by amyloid plaque. The black bars represents AP mice, which are Alzheimer's disease mouse model, and the gray bar represents AP mice with overexpressed AAT2, also known as GLUT1. This figure shows that when there's overexpression of GLUT1 expression, there's decreased amyloid plaque accumulation in these regions of the hippocampus. In addition to glutamate transporters being dysregulated or decreased, glutamate receptors are also decreased, leading to altered energy metabolism. Metabotropic glutamate receptor 5 is one of the key receptors on neurons. It can bind to glutamate and amyloid plaques. The receptor doesn't bind directly to amyloid plaques. It indirectly binds with prions, which are attached to amyloid plaques. Once the receptor has been activated by glutamate or amyloid plaques, comodulin kinase 2 can be activated. Overall, glucose metabolism, lipid metabolism, and glutamate metabolism have been shown to be dysregulated in Alzheimer's disease patients. Understanding the molecular biology behind these changes can serve as biomarkers and therapies for future or for treatment for Alzheimer's disease. Current treatment only addresses symptoms of Alzheimer's disease, such as depression, which is addressed by Zyprexa. Therapies can revolve around correcting the enzymatic activities or correcting the expression levels and activation of key enzymes, receptors, and transporters. Before I end, I would like to acknowledge the Biomolecular Sciences Master's Program at Lipscomb University and Dr. Mara Sledge. These are my references. Thank you for listening, and are there any questions?